So this video is going to give a recap of moles and the different aspects of how we use it. So when we think about how things are measured, one of the most common ways to measure is using mass, which usually uses the units grams. However, in chemistry that's not always very useful, because if we say 1 gram of a substance, that's going to be different for each substance in terms of comparing the number of atoms. And in chemistry all we really care about is those rearrangement of atoms, or how many atoms of one thing is reacting with the atoms of another thing. So it wasn't very useful for comparing the amounts of substances for elements, and so instead chemists have to come up with something else. And so they came up with the mole, and it's the main unit of measurement for chemistry. The name mole actually comes from the German word for molecule, which is Molekül. That's why they call it mole. And the mole itself is the amount of any substance that contains as many elementary entities, so that's atoms or molecules or ions or units, anything like that, compared to 12 grams of pure carbon-12. So when they look at 12 grams of pure carbon-12, they're using that as a benchmark to compare other stuff, and that's a constant, so they call it Avogadro's constant, and the number of atoms in 12 grams of pure carbon-12 is 6.02 times 10 to the 23. And we use the capital N-A to signify Avogadro's constant, to use that to compare to other substances in order to calculate how much moles or how much of that substance there is. So really the mole is a relative term. It's saying it's everything relative to 12 grams of pure carbon-12. And so Avogadro was an Italian scientist who developed this constant, and he did a lot of work around moles and quantifying the ratios. And so the idea is we're saying, okay, the number of moles is going to be the amount of a substance divided by Avogadro's number, or in relation to Avogadro's number. And so the one formula we use is that little n for moles, with the units mole, M-O-L. Capital N is the number of some sort of elementary unit, such as atoms, molecules, ions, or just units. And then we divide it by Avogadro's constant, which actually has units as well, and its units are mole to the -1. And if we have one of those magic triangles, we can also see in order to rearrange our equation. So one quick example question. Mr. Whedon wants to give his bug Pokemon iron to raise its base defense stat. Determine how many moles is in a sample of iron if it contains 6.86 times 10 to the 23 atoms, and give your answer to 3 significant figures. So in our equation, we know that capital N is going to be 6.86 times 10 to the 23. We're going to divide that by Avogadro's number, and what we get left over is 1.1395, but since we have to do it to 3 significant figures, really the answer is 1.14 moles. So I'm going to put a practice question up on the screen. Mr. Kim is on his 3rd cup of coffee for the day. How many atoms of caffeine are present in his cup if he has 2.34 moles in the cup? And give the answer to 3 significant figures. Pause the video, have a go, and then I'll put the answer up. Okay, so the answer to this one, we rearrange our formula to get capital N equals little n times Avogadro's number. So 2.34 times 6.02 times 10 to the 23 gives us that big number of 14.0868 times 10 to the 23, which is rounded to 14.1 for our 3 significant figures, times 10 to the 23 atoms. So the real problem though is that in our everyday lives and even in our chemistry lives, we don't like to look at how many atoms of something is reacting. So it's not actually very useful to count things in atoms or use atoms. So instead we try and use something that's a bit more useful. And as we said, the most common form of measurement is with mass. So we can also calculate moles using mass and using molar mass. So molar mass meaning the number on the periodic table underneath an element symbol, which is the molar mass or given molar mass for that element. And the relationship between those 3 things is this. So little n equals mass over molar mass, and we've got a magic triangle for that as well. And the idea is this helps us get an idea of the units for mole, because our mass, as we said, was in grams. molar mass is in grams per mole, and so by going grams divided by grams per mole, the grams cancel out, mole gets flipped, and we get just mole. Don't worry too much about how to get those units. The important thing is just that those are the units for moles. So another example question. So Miss James wants to give a 45.691 gram sample of calcium to her Flareon to raise its base special attack stat. How many moles of calcium would Miss James be giving her Flareon? And giving the answer to 3 significant figures. So following our equation, first we need to actually work out the molar mass of calcium. So looking at our periodic table, it's 40.08 grams per mole, or G dot mole to -1, same thing. So we've got N equals mass on molar mass, which is 45.691 divided by 40.48. So that gives us 1.139995, but because we have to give our answer to 3 significant figures, that becomes 1.14 moles. So another practice question for you guys. So coughing produces toxic gases which are flammable, such as H2S, hydrogen sulfide. Calculate how many moles of H2S is present in 23.21 grams of gas, given off to 3 significant figures. Pause the video here, and then on the next slide I'll go through the answers. So first thing we need to do is calculate molar mass. Molar mass will be 2 lots of hydrogen plus sulfur, which ends up being 34.076 grams per mole. And then even though that itself we want to find to a certain number of significant figures, we need to make sure to use the whole value for any subsequent calculations. So save it in your calculator, because when we do our N equals mass divided by molar mass, we need to use the whole number to get a more accurate answer at the end. So finding number of moles, it's going to be 23.21 grams, which was the mass that we wanted, divided by the molar mass, gives us 0.68112. We round that to 3 significant figures, gives us 0.681 moles. So those are 2 main equations involving moles, and the main ones we looked at in year 11. We also learned another one in year 11, which we're going to look at on the next slide. However, we do need to know kind of how to manipulate this one the most. In year 12, we don't really look at this one very much at all. This is the most important one. However, we will also be looking at molar concentration. So this is the last thing we're going to look at right now. And the idea is that we deal as chemists with powders and with solutions. And so when we're looking at a solution of some sort of chemical, we want to know the concentration. And the concentration is dependent on the number of moles inside that concentration. If we're talking about what concentration is, it's the quantity of solute, so of some sort of powder, dissolved in a set volume of solvent. So solute plus solvent equals a solution. So solute are the little particles, and then we dissolve it in a solvent, and it all gets mixed together to make the solution. So the more little particles of solute you have, the more concentrated it is in a given volume. The less solute, the less concentrated. So if you've got more little particles, you've got more moles, or you've got a higher number of atoms. So what we're looking at is a more concentrated solution will have more moles in it. Molar concentration is directly related to moles. The units are moles per litre, and it represents the amount of moles dissolved in that set volume. So this is the formula overall, and we can condense it down to C equals N on V. So it means concentration of the solute is equal to the number of moles of the solute divided by the volume of that solution in litres. This is the most commonly used unit of concentration. There are a few others. We do need to know how to convert them, but that's for another time. And again, we've got a magic triangle to help us out with that. So C equals N on V, N being at the top of the triangle. So the units for molar concentration can be written in a few different ways. Mole divided by litres, mole dot L to the -1, or even just a capital M. That capital M, if it's after a number, it's a unit. If it's before a number, it's a molar mass. We need to make sure we know this distinction. But you can use any of them when doing molar concentration. So an example question. A year 12 student is staying up late to finish an assignment and makes a cup of coffee by adding 1.52 moles of caffeine to 250 mils of distilled water. We're assuming it's distilled. They're probably not drinking distilled water. Do not recommend you do that. However, to make it easier for the chemistry, we're assuming distilled water. So the question is, what is the concentration of the caffeine? So for this question, we need to use our formula. So C equals N on V. Our N is 1.52. Our volume, it's given to us in mils in the question, but we need to convert that to liters. So converting it to liters will be 0.250 liters. So overall the answer should be 6.08 moles per liter, or capital M for molarity. Here's a practice question. What is the molar concentration of the solution prepared by dissolving 10 grams of sodium hydroxide powder to make a 150 ml solution of sodium hydroxide? Going to 4 significant figures. So pause the video, have a go, and then have a look at the answer. So using our N equals M on molar mass, first we need to know how many moles are in a solution, or in that 10 grams, sorry, to know what the concentration is going to be. So first we say, okay, we're going to do the mass of sodium hydroxide powder divided by the molar mass. Mass is 10 grams, the molar mass is 39.998 grams per mole, and so that means that we've got 0.250 moles of sodium hydroxide powder that we're putting into that solution. So now that we know the number of moles, we can use our C equals N on V. So N is 0.250, volume was 150 mils, so that's going to become 0.150 liters, and so altogether we're going to have a concentration of 1.667 moles per liter. Now ignore my animations for this, I got it around the wrong way, that's alright. So the question or the scenario is that a student wants to make sure that they have the right amount of sodium in their water to maximize electrolyte consumption to tackle the staircases of AHS, because they're everywhere and you have to go up and down all day. If the molar concentration of sodium in a Powerade bottle is 0.02366 moles per liter, how many grams of sodium powder needs to be added to a 750 ml bottle and filled with water to get the same concentration as that Powerade? So pause the video, have a go, and then have a look at the answer. So we've got our C equals N on V, but we rearrange it to see what number of moles we need. So the idea is we've started off with this concentration, so we have a known concentration, we have a known volume, so in order to find mass we have to work backwards, so N equals C times V, so the number of moles is going to be the 0.02366 moles per liter times by 0.750 liters. That's going to make 0.017745 moles. So remember, not rounding up the number yet, using that whole number for further calculations. And so the mass is going to be N times capital M, so our molar mass here. Remember, it's only moles per liter if it's after a number. And so it's going to be 0.017745 moles times by the molar mass of sodium, which is 22.99 grams per mole. And so the mass of sodium needed for this is 0.4080 grams. Okay, so that's it for this video. We'll talk about it more in class as we go.